For us, very important one is semiconductors. These semiconductors are classified into two categories. Intrinsic semiconductors or pure semiconductors. Intrinsic semiconductors are pure semiconductors. The second one is extrinsic semiconductors or impure semiconductors. These extrinsic semiconductors or impure semiconductors once again classified into two categories. N-type semiconductor, P-type semiconductor. N-type semiconductor and P-type semiconductor. Now first we will start with the intrinsic semiconductor or pure semiconductor. Pure semiconductor or intrinsic semiconductor. This is example for this pure semiconductor is silicon and germanium. Is nothing but intrinsic semiconductor or pure semiconductor. Now what is its properties? What is this one? We will see now. For that purpose we require a crystal structure. Okay, it's a it's a three-dimensional view. Okay, we are going to see it. So take it as a silicon or germanium. For simplicity purpose, I will take it as silicon. There are 4 valence electrons. It's a fourth group element. Silicon and germanium are fourth group element. That means it will have 4 valence electrons. The previous shells are fully occupied, but the outermost shell is having 4 valence electrons. So it's a neutral. Actually, any crystal is a neutral. So I have represented negative charges, electrons outside. Therefore, I am indicating +4. +4 minus 4 is a neutral, silicon. The next it's silicon +4. 1, 2, 3, 4. Simply now I am indicating it's only +4. It's nothing but silicon. Now, what is going to happen now? These are silicon atoms, are there? For a stability purpose, each atom requires 8 valence electrons, but there exists a 4 valence electrons only. So what is going to happen is, these 4 valence electrons forms a covalent bonds with the 4 neighboring atoms. So this valence electron forms a covalent bond with this valence electron. It's sharing covalent bond. This is another covalent bond. This is another covalent bond. This is another covalent bond. Now see this one. How many valence electrons are there? 1, 2, 3, 4, 5, 6, 7, 8. Got the stability or not? Always their atoms aim is to get the stability. Now 4 valence electrons will share or forms a 4 covalent bonds with the neighboring atoms, nothing but they are sharing the electrons, valence electrons. Therefore, stability is achieved. Similarly, this also forms covalent bonds with this one. Actually, if you draw this one, it's a 3-dimensional. Therefore, here one more atom will be there like this. Similarly, all these right now forms a covalent bond with the neighboring atoms. Therefore, it is stable. This forms next like this. next like this, next upper or back side like this. Clear? If you see in this one, all atoms forms a covalent bonds with the neighboring valence electrons. So all atoms are stable. Any free electron is available? No free electron is available. Free electron is not available means it is conductor or in semiconductor or insulator. No free electron is available. Therefore, it is a insulator. Therefore, already I said semiconductor at 0 degree Kelvin, at absolute 0, that's nothing but at 0 degree Kelvin, acts as an insulator because there is no availability of charge carriers. Clear? First point. Now, temperature is increased. That means thermal and room temperature. Okay, 27 degrees centigrade. That is nothing but 300 degree Kelvin. That means you are supplying the thermal energy. Temperature is increasing means thermal energy is given. Thermal means temperature. Thermal energy is given. Because of the thermal energy, some of the valence electron may acquire the energy to become a free electron. Let us suppose this electron acquires the energy, so it becomes free electron. Now absence of electron becomes hole. So this is hole, this one is free electron. Is clear? This is free electron, this is hole. Let us suppose one more covalent bond is broken, this becomes free electron. Now here absence of electron is hole. Assume there is one more covalent bond is broken, here hole will be formed, here electron is formed. So how many holes are there? 1, 2, 3. How many free electrons are there? 1, 2, 3. Therefore, as temperature increases, what happens to some of the covalent bonds? Some of the covalent bonds will be broken. Some of the covalent bonds are broken. That means electron, that's called free electron hole pair is generated. Free electron hole pair is generated. Now if you see how many electrons are there here, free electrons 3. How many holes are there? 3. Therefore, in this intrinsic semiconductor or pure semiconductor, number of electrons is equals to number of holes. In a pure semiconductor and intrinsic semiconductor, number of electrons is equals to number of electrons in the sense always, I said the number of electrons, default assume it as a free electron. If it is a valence electron, I will explicitly mention it as a valence electron. Otherwise, if I mention it as an electron means default assume it as a free electron. If it is a valence electron, I will pronounce it as, I will give it as valence electron. So, for an intrinsic semiconductor, number of electrons is equals to number of holes. Okay. Now, what is the disadvantage of this pure semiconductor? The number of charge carriers, that's electrons and holes, are very small. Because of small number of electrons and holes, conductivity is very less. Conductivity is very less. That is the disadvantage. Conductivity is very less. This is the disadvantage of pure semiconductor or intrinsic semiconductor. To overcome this disadvantage, we are going for impure semiconductor or extrinsic semiconductor. Impure semiconductor or extrinsic semiconductor. What this intrinsic impure semiconductor is going to do, we'll see. Why we are going for impure semiconductors? To increase conductivity. To increase conductivity. We are going for impure semiconductors. Now, how to increase the conductivity? We are taking a silicon or germanium. We are adding impurities. That resulting is called impure or extrinsic semiconductor. We are taking either silicon or germanium, we are adding impurities, the resulting one is called impure or extrinsic semiconductor. The process of adding impurities is called doping. The process of adding impurities is called doping. Clear? Now, the impurities that can be added are either third group elements or fifth group elements. Third group element example are boron, aluminium, gallium, okay, like this. Fifth group elements are phosphorus, arsenic, antimony, okay, like most commonly used is phosphorus. The second one is arsenic. Here the most commonly used either boron or aluminium. Because if you go as top, the conductivity increases. Okay, that's why here these two are most commonly used one, here these two are most commonly used one. So to increase the conductivity, we are going for adding impurities to the pure semiconductor. The resulting one is called extrinsic semiconductor or impure semiconductor. The process of adding impurities is called doping. What is the need for doping? To increase the conductivity. What are the impurities that can be added? Either you can add fifth group elements or you can add third group elements. If you add silicon, if you take silicon or germanium, add fifth group elements, the resulting semiconductor is called N-type semiconductor. The resulting semiconductor is called N-type semiconductor. Take a silicon or germanium, add third group elements. The resulting semiconductor is called P-type semiconductor. The resulting semiconductor is called P-type semiconductor. Now we'll start with the first one is N-type semiconductor. N-type semiconductor. Here we are adding fifth group elements. Fifth group elements are added. Example, phosphorus, arsenic, okay, most commonly used one. Now if you add phosphorus to a silicon, what is the crystal structure? And we are adding 1 part in 10 power 8. The doping concentration is 1 part in 10 power 8. What is the meaning of 1 part in 10 power 8? For 10 power 8 phosphorus atoms, sorry, for 10 power 8 silicon atoms, for 10 power 8 silicon atoms, 1 phosphorus atom is added. That is called 1 part in 10 power 8. For 10 power 8 phosphorus silicon atoms, 1 phosphorus atom is added. Okay, that's called 1 part in 10 power 8. Now comes to the crystal structure. take this as a silicon, we are indicating it as one part in phosphorus, it is having 5 valence electrons, indicating like this. Now less number of phosphorus atoms, more number of silicon atoms. Therefore we are taking a 3-dimensional, taking one point here, one phosphorus atom is there, the surrounding are silicon atoms. Here plus 5, here plus 4. Okay. Similarly here plus 4. So now what is going to happen? It's a 3-dimensional, its extension is there, that's whatever we have taken on a 2-dimensional plane paper. This forms a covalent bond for stability purpose, forms a covalent bond, stability, covalent bond, covalent bond, covalent bond, covalent bond. Now, at room temperature, before going for room temperature, now see here, phosphorus atom is having 5 valence electrons, 1, 2, 3, 4, 5. These, out of these 5 valence electrons, 4 valence electrons forms a covalent bond with the 4 neighboring silicon atoms to achieve the stability. Now what about this one? It is not formed any covalent bond. It is not formed any covalent bond. Now, what is this forbidden energy gap? Indicates the amount of energy required to move an electron from the valence band to conduction band, which is, this is nothing but Eg, which is approximately equals to 1 electron volt, we know already. That means if you give around 1 electron volt, this covalent bond is broken, this free valence electron becomes a free electron and whole pair is generated. Now this is not formed, any covalent bond. Then how much energy has to be given to becoming it as a free electron? Whether this energy required to make this free electron as a free electron is equal to amount of energy required to make this electron as a free electron? No. Very small energy is sufficient to make this electron as a free electron. You don't require 1 electron volt, very small. How much? That is 0.05 electron volt is required if it is a silicon, 0.01 electron volt is required if it is a germanium. Now what is the meaning of that thing? If you give for this valence electron approximately around 0.05 electron volt, it becomes a free electron if it is a silicon. If it is a germanium, only 0.01 electron volt is sufficient, which is easily obtained. Therefore, no need of going for room temperature. At very small temperature, at what we can say nearer to 0 degree centigrade, or 0 degree Kelvin, this electron acquires the energy and becomes free electron. Now we know this much gap is required, that is 1 electron volt, but here is only 0.01. How to differentiate? For that purpose, here we are going to indicate one energy level known as donor energy level. What is this donor energy level gap? This gap is equals to 0.01 electron volt if it is germanium, 0.05 electron volt if it is a silicon. So this electron becomes a free electron, nothing but it goes to conduction band if you give 0.01 or 0.05, that depends on either silicon or germanium. Is clear? So now the important thing is, you given 0.01 electron volt, this valence electron becomes a free electron, whether hole will be created or not. No hole is created. Hole will be created if you break the covalent bond and free electron hole pair is generated, else no hole will be created. Clear? That's another important point. Now this electron become a free electron, this valence electron has become a free electron by giving a small amount of energy, and since covalent bond is not broken, therefore hole is not generated, whereas electron is generated. Now at room temperature, what is going to happen? This covalent bond is broken. Assume that here hole and here electron, free electron. Let us suppose this covalent bond, some covalent bond, okay, this covalent bond is broken, this electron becomes a hole and free electron. Now how many free electrons are there? 1, 2, 3. How many holes are there? 1, 2. I have taken a small number, small figure. Here only number of electrons are more than number of holes. If you take like this 5 into 10 power 23 atoms per centimeter cube, 1 centimeter cube I will have 5 into 10 power 23. If you take that many, we will have so many number of electrons and so many number of holes. And in n-type semiconductor, see 1, 2, 3 electrons, 1, 2 holes. Therefore, in n-type semiconductor, I will write it here. In n-type semiconductor, electrons are greater than holes. These are called, electrons are called majority charge carriers. Majority charge carriers. Holes are called minority charge carriers. Okay. Electrons are called majority charge carriers, holes are called minority charge carriers, and number of electrons are more than number of holes. Now my question is, okay, the next another point is, the fifth group elements, the phosphorus, arsenic, antimony, are also called as donor impurities. Donor impurities. The fifth group impurities or fifth group elements, that's phosphorus, arsenic, antimony, are called donor impurities. Why these are called donor impurities? They will donate, you see, here 5 electrons are there, it's donated 1 electron. The remaining 4 forms a covalent bond, they are attached, they are with this one only, but the fifth one is left this atom, okay. Therefore these are called donor impurities. Now my next question is, majority charge carriers are electrons, minority charge carriers are holes, electrons are negative charge, holes are having positive charge. Since negative charge is more than positive charge, is it electrically negative or electrically positive or electrically neutral, or we can't say? More amount of negative charge, electrons are more, so negative charge is more than positive charge. Therefore, is it electrically positive or electrically negative or electrically neutral or none of the above, or we can't say? It is electrically neutral. Why it is electrically neutral? See, in the same example, how many electrons are there? 3 electrons. These electrons are having negative charge. Negative charge. How many holes are there? See, in the same one, 1, 2. 2 holes are there. Positive charge. Any other thing in this figure? See this one. It's donated one electron. Donated one electron means it becomes ion. Whether it's a positive ion or negative ion, donated one electron, deficient of one negative charge. Therefore it becomes positive ion. How many, one donated one electron means it becomes a positive ion. How many ions are there in this figure? One ion. So one positive ion, and it is having positive charge. So total positive charge is 2 plus 1, 3, negative charge is 3, therefore overall it's electrically neutral or not? Therefore n-type semiconductor is electrically neutral. Similarly in intrinsic semiconductor or pure semiconductor, number of electrons is equals to number of holes. So positive charge is equals to negative charge, therefore that is also electrically neutral. So n-type semiconductor is neutral, intrinsic semiconductor is neutral. What about these conductors? There are so many free electrons are there. At the same time there also ions will be there. That is, conductors also electrically neutral. All the materials are electrically neutral at any point of time. Clear? So this is n-type semiconductor is also electrically neutral. Next comes p-type semiconductor. Take a silicon, add third group elements, then the resulting one is called extrinsic semiconductor and it is called p-type semiconductor. What are the third group elements? Boron, aluminum, gallium, indium, like that. Now we will take a crystal structure of the p-type semiconductor. Here we will take one boron. It's a third group element, therefore 3 valence electrons are there. It's surrounded by silicon atoms. It's plus 4. This forms covalent bond, this forms covalent bond, forms covalent bond, like this. Now to form a covalent bond, here one electron is required. There is a strong tendency that it will pull some valence electron from the neighboring atom. Okay, so there hole will be created, here electron comes. That means indirectly here we are taking it as absence of electron. and like this. There is a strong tendency to form a covalent bond. Therefore, here we are taking absence of electron, that's nothing but a hole to form a covalent bond. Now, in this figure, at this instant of time, how many holes are there? One hole. How many electrons are there? 0 electrons. Okay. Now temperature increased. Temperature increases means some of the covalent bonds are broken. So this electron becomes a free electron, means here hole, electron hole pair is generated. Similarly, electron hole pair is generated. Now how many holes? 1, 2, 3. How many electrons? So right now in this figure there are 3 holes are there, 2 electrons are there. Therefore, holes are majority charge carriers, electrons are minority charge carriers. Holes are majority charge carriers, electrons are minority charge carriers. Now, more positive charge than negative charge. Is it electrically positive or electrically neutral? It is also electrically neutral. How we are going to say it's electrically neutral? It's accepting an electron to get the stability. Accepting an electron means there are 3 holes will be there, 2 electrons, plus accepting one electron means accepting one negative charge. That means it becomes one ion. This one negative ion. Therefore, this is negative charge, this is positive charge, electrically neutral. Now, coming to the energy band diagram. Here absence of electron, okay, how much energy required to attract one electron? Okay, it's not equals to 1 electron volt. To attract 1 electron volt, generally it requires 1 electron volt. To excite or to attract 1 electron volt, normal case. But here there is a strong tendency to get the stability, 1 more electron is only required. There is a strong tendency, that means small amount of energy is sufficient to attract 1 electron from the neighboring atom. Therefore there is one energy level called as acceptor energy level existed just above the valence band. That means if you give that much of energy, 1 electron free electron becomes a valence electron. How much that is required? Once again it is equals to 0.05 electron volt if it is a silicon, if 0.01 electron volt if it is a germanium. That acceptor energy level is 0.05 electron volt if it is a silicon, 0.01 electron volt if it is a germanium. Is it clear? Therefore, in p-type semiconductor, majority charge carriers are holes, electrons are minority charge carriers, and there are ions will be there. Therefore, it's electrically neutral. There exists an acceptor energy level just above the valence band. That acceptor energy, that is called acceptor energy level. It's equals to 0.01 electron volt if it is germanium, 0.05 electron volt if it is a silicon. Clear? Now, there are so many number of electrons, holes are there, therefore conductivity increases. That's why we are going for adding the impurities. That's called, we will get the extrinsic semiconductor. Now next one is drift. Okay. Now already I explained, take a metal, there are so many number of free electrons are there, they are moving in a different directions, so net current at any point of time is equals to 0. If you apply a field like this, all the electrons are moving in this direction, therefore current is flowing in this direction. This current is called drift current. This current is called drift current, and this is called drift current. This is called current density. What is current density formula? It is current by area. Current by area. Drift current density. Drift current density is equals to drift current density is given by N mu N E E. What is this E? Is applied electric field. Total number of electrons, charge of electron, mobility of electron. Total number of electrons, mobility of electrons, charge of an electron, applied electric field. This is called drift current. Next. Now this is for conductors. This formula is for conductors. What about for semiconductors? The same phenomena is existed. Electrons will be there, but at the same time holes also will be there. For a semiconductor, electrons will be there, holes will be there. Total current equals to electron current plus hole current. Therefore, J drift current equals to J drift due to holes plus J drift due to electrons. It's summation. Total current equals to electron, current due to electrons plus current due to holes. Now why it has to be added, why it should not be subtracted? Hole L is moving in the direction means, hole is moving in this direction means, electron is moving in this direction. So it has to be subtracted or not? Okay, it's not like that. Holes are moving in this direction means, current due to holes is in this direction. Electron is moving in this direction means the current is opposite direction to the electron movement. Therefore, current due to electrons is equal. Therefore, total current is equals to summation of hole current plus electron current. Therefore, the current density J drift equals to J drift due to holes plus J drift due to electrons. What is this holes? Its number of holes equals to, I assume it as P. This is mu P, mobility of hole. Charge of electron is equals to charge of hole. Therefore, it's same. Applied electric field is E. Same N mu N E E. This is called J drift. So take P mu P E plus N mu N E outside. Okay, this is called J. This is called sigma into E. Current density, drift current density equals to sigma into E. It's applied electric field. Now, this is called Ohm's law. V equals to IR is one of the Ohm's law. Okay, that is in terms of voltage current. Okay, in terms of current density, electric field and conductivity, this is the formula. J equals to sigma E. Now what is J? Current density. What is E? Applied electric field. What is sigma? Sigma is called conductivity. Very, very important for problems point of view. These formulas are very, very important. So now what is this one? This is nothing but sigma. Sigma equals to P mu P E plus E plus N mu N E. Is clear? It's called conductivity. Next one is, one more formula is resistivity, is denoted as rho. Resistivity, rho. That is 1 by conductivity. 1 by conductivity is called resistivity. All these formulas are very, very, very important. Units for resistivity are ohm, centimeter. Ohm, centimeter. Units for conductivity, mho per centimeter or Siemens per centimeter. Clear? There is one more formula, resistance R. This is called resistivity, this is called resistance. Resistance R equals to rho L by A. Units are ohms, where L is length, A is area. This is resistivity. So this is one formula, these are units. This is one more formula, this is one more. Then sigma equals to this one. All these are very, very important. Clear? Next. So in metals only drift current due to electrons will be there. In semiconductors, drift current due to both electrons and holes will be there. Therefore, total is summation of drift current due to electrons plus drift current due to holes. The next mechanism is diffusion. Diffusion. Now take some material, either a silicon or a germanium or a metal, something. Let us assume that the distribution of, I taken a metal, assume the distribution of electrons are like this. The distribution of electrons, I have taken example metal. Or instead of metal, better go for a semiconductor. Okay, take a semiconductor. We are having more number of this is an imaginary surface. This is x equals to 0. Here x is increasing, distance is increasing. Now, if the charge carriers are distributed like this, immediately there is a movement of charge carriers from high concentration area to low concentration area till equilibrium is reached. If the charge carriers are unevenly distributed as shown in this figure, one side of the imaginary axis more number of charge carriers, other side we are having less number of charge carriers, then automatically there is a movement of charge carriers from high concentration area to low concentration area till equilibrium is reached. What is meant by equilibrium? That means all the, in the entire semiconductor, entire bar equally distributed charge carriers. That means here whatever the number of electrons are there, here also same number of electrons are there. They are equally, uniformly distributed. That's called equilibrium. So there is a movement of charge carriers from high concentration area to low concentration area till equilibrium is reached. Clear? Now electrons are moving means current will be there or not? That current is called diffusion current, and the current density is called diffusion current density. Diffusion current density. It's clear? That is called J diffusion. Now diffusion to occur, what is the minimum requirement? Drift to take place means drift current has to exist, and means compulsory external electric field is required. Diffusion has to be taken means any external field is required? Any external field is required? No external field is required. What is the requirement? Simple. One side more number of charge carriers, other side less number of charge carriers. Charge carriers in the sense either it can be electrons or it can be holes. One side we are having more number of holes, electrons, other side we are having less number of holes, electrons. That is called concentration gradient. That is called concentration gradient. What is the meaning of concentration gradient? The number of electrons or holes are going to change with respect to distance. This, in this case example, it is dn by, it's called dn by dx. Okay, this J diffusion due to electrons is given by E dn by dx. Similarly, same concept, if holes means they will move in the opposite direction. That means here more number of holes are there, here less number of holes are there, means they will move in this direction. Or here more number of holes, here less number of holes, holes also will move. Holes or electrons will move from high concentration area to low concentration area till equilibrium is reached. Electrons or holes are changing means, moving means, current will be resulted. This J diffusion due to holes is given as minus P dP dP by dx. What is this? Minus E. E means charge. E is charge. This is called diffusion constant for electrons. Diffusion constant for holes. Concentration gradient of electrons. Concentration gradient of holes. J diffusion equals to E dn by dx. J diffusion due to holes equals to minus E dP dP by dx. This is called concentration gradient of holes, concentration gradient of electrons, diffusion constant for electrons, diffusion constant for holes, charge of electron, charge of hole. Clear? So diffusion has to take place means the only requirement is internal concentration gradient. Drift has to be taken place means external electric field is required. In metals only drift mechanism will be there. In semiconductors both drift mechanism will be there, diffusion mechanism will be there. In semiconductors both electrons and holes will be there. In metals or in conductors only holes, electrons will be there. Okay, that's the difference between the conductors and semiconductors. Now, if I want total current density, total current density, J total is equals to current density due to holes plus current density due to electrons. Now current density due to holes is equals to current density due to drift holes plus current density due to diffusion holes. Similarly, J due to electrons, current density due to electrons is equals to J drift due to electrons plus J diffusion due to electrons. So summation of all these 4 is equals to total current density. Now what is this drift? P mu P E into E. This is drift current due to holes minus E dp by dx. This is diffusion current due to holes. This one N mu N E plus E dn by dx. Is clear? This is called this. Next. So this about the current density. Now what is this mu? Mu is called mobility. Now what is the meaning of mobility? How freely the electron or hole is moving. Mu n, mobility of electron, how freely electron is moving. Mu p, mobility of hole, how freely it is moving, hole. Now whether this mu n and mu p both are same or different. Take down this one, it's a nucleus, hole will be there here, free electron is here. Free electron can move randomly any direction or not. So mobility for this one is higher or not? This is, it's under the nucleus force, it cannot move whatever the way it wants. It has to move according to the, within the nucleus force, it has to be in this one only. Whereas your free electron can move in any direction. So this can move freely but it cannot move freely. It has to move within this one. Therefore, mobility of electron is more than mobility of holes. Mobility of electron is more than mobility of hole. If we see silicon, germanium mobility of electron, mobility of hole, there is one tabular column. Mobility of holes, 1 minute, here it's also. This is germanium, this is silicon. Okay. See here, mobility of electron is 3000. In germanium, if it is in silicon, it's 1800. Whereas holes, mobility is in germanium, it's 1300, silicon it's high. Okay. Now see here, electron mobility is more than hole mobility or not? Electron mobility is more than hole mobility or not? It's around 2.5 times approximately. Mobility of electron is approximately 2.5 times that of the mobility of hole. And mobility of germanium is more than mobility of silicon. In silicon, mobility is less compared to germanium. Why? Silicon atomic number, if you see, it's smaller one compared to germanium. So germanium is far away from the nucleus force. Silicon is nearer to the nucleus, therefore it's more attracted by the nucleus force. It's very difficult to have a movement, whereas in germanium it's far away, therefore germanium mobility is more than in germanium mobility of electrons and holes is more than mobility of electrons and holes in silicon. And in that one, mobility of electron is more than mobility of hole, approximately around 2.5 times. Is clear? Next one is the units for mobility is centimeter square per volt second or meter square per volt second. One of the gate question. Units for mobility is centimeter square per volt second or meter square per volt second. The next one, as temperature increases, what happens to mobility? Mobility decreases. Mobility is proportional to T power minus 3 by 2 on an average. It will change for silicon, germanium, electron, holes. It's continuous, it's still changing. But an average mobility is, as temperature increases, mobility decreases. The relationship between mobility and temperature is mu is proportional to T power minus 3 by 2. Next. There is one relation known as Einstein relationship. Which is also important for problems. dP, diffusion constant for holes, by mobility equals to dN by mu n equals to Vt. What is Vt? Volt equivalent temperature. Okay, this equation is called Einstein relationship. Here what is Vt? It's T by 11,600 or 26 millivolts at room temperature, or this Vt is called K bar T, or it is also called as Kt by Q. What is K and K bar? K or K bar is called Boltzmann constant, where K or K bar is called Boltzmann constant. Okay. Now what is the difference between K and K bar? Okay, I will give that formula. K equals to 8.62 into 10 power minus 5 electron volt per degree Kelvin. Boltzmann constant is 8.62 into 10 power minus 5 electron volts. K bar equals to 1.38 into 10 power minus 23 joules per degree Kelvin. Per degree Kelvin. 1 electron volt is equals to 1.69 into 10 power minus 9 joules. 1 electron volt equals to 1.69 into 10 power minus 9 joules. Minus 9 joules. Minus 19, sorry. It is 1 electron volt equals to 1.69 into 10 power minus 19 joules. In electronics, generally joules is the unit, but in electronics, the joules is a too large quantity. To make it as a requirement for small one, we are having 1 electron volt. We will use generally electron volts in electronics, because joules is a bigger quantity. Therefore, what is 1 electron volt? 1.69 to 10 power minus 19. Okay. The next. Now we will have a break. After break we will continue with the remaining things. In the valence shell, it is not responsible for current. Yes, we'll continue with the questions. Kirtana, sir, is valency electron having charge? Whether electron is a valence shell or free electron, it will have charge. It will have charge, compulsory. Whether it is responsible for current or not, that depends on whether it's a free electron or valence electron. Charge will be always existed. It's clear, Kirtana? If it is in the valence shell, it is not responsible for current. Clear, Kirtana? Pooja, why did you write +4 in silicon in intrinsic semiconductor? I mean that, what is the meaning of 4, +4? Yes, I got it, your question. Take a silicon. It's a neutral. I said all the materials are neutral. That means total positive charge is equals to total negative charge. Clear? I have indicated like this. Now what I have done? 1, 2, 3, 4. 4 electrons I have shown explicitly or not? That means is it having 4 negative charge? I have explicitly shown 4 negative charge, 4 electrons. That means negative charge is -4? No. It's a neutral. Therefore, I have to explicitly represent it as +4. What is the meaning of this thing? +4 -4. It's a neutral. Otherwise, you can indicate like this. That's a neutral. But we have required the covalent bond has to be formed. That's why we have taken 4 valence electrons. 4 negative charge is shown externally. Therefore, to counterbalance it as a neutral, you are indicating +4. So 4 negative charge, 4 positive charge. It's a neutral. Clear, Pooja? Next, it's Piyush Binani. How does the imperfections is defined for a crystal and how it affects the properties of crystal in terms of conductivity and resistivity? Okay. That thing will take it in problems. While explaining, we will add a impurity. What is going to happen? We are going to see that one. That I will explain in the next session. Okay, Piyush. Next, why we use ultra pure silicon crystal for fabrication? As you told, its conductivity. It's ultra pure silicon crystal. But where I said ultra pure, okay, actually it's a pure silicon crystal for fabrication. As you told, its conductivity is very less. Yes, good question, but we are going to see it in VLSI. Okay, in the last sessions we are going to see whatever your question. Why you have to take a pure silicon crystal for fabrication? Fabrication comes in VLSI. Right now there is no need of that much purity. Clear? Yes, whatever that comes in VLSI. Clear, Piyush? Next, Pooja. Why in phosphorus atom extra electron does not generate holes, but in intrinsic you consider hole when electron is leaving? Okay. Now, why in phosphorus atom extra electron does not generate holes, but in intrinsic semiconductor consider electron hole when electron is leaving? Now one important point is, see here, there are 4 electrons, it forms a covalent bond with this one. Okay, when you break the covalent bond, then only electron hole pair is generated. Without a bond, either it's a ionic bond or covalent bond, if you break it, it is not going to have a whole electron pair. Now the 5th electron, it's not covalent bond is not formed, therefore it becomes electron, free electron, no need of hole. If you break the covalent bond, yes, it will generate. Now in intrinsic semiconductor, if you see, I have taken here silicon, here also I have taken silicon. There is a covalent bond is there, covalent bond is broken, therefore it's a free electron hole pair is generated. Without covalent bond, no problem. But if covalent bond is broken, electron hole pair is generated. Is clear, Pooja? If any of the four covalent bonds are broken, electron-hole pair will be generated. Fifth, unattached electron becomes a free electron without creating hole. That is the difference. Clear, Pooja? Next, Sykert-Coley. In p-type extrinsic semiconductor, the hole forms the bond. Yes, but I guess it should be electron of silicon and boron will form the bond, and that electron of boron will come from some of free electron of silicon. Am I correct? Okay.